All right, thanks, Soren. Well, so I'm going to talk to you a bit about my research and basically my work in open information extraction. Well, you may have noticed that I put open in parentheses, and you'll get soon why I'm doing this. And also, you may have noticed that I'm actually framing this talk as a question, because, well, besides presenting the work that I've done, what I would like to do with this talk is like to let us step back a bit and have a different perspective on open information extraction. So, well, before we start, a little bit of presentation. Well, that's my content over there. I'm a second-year PhD student at Sapienza University of Rome. I work in the LCL group with Professor Roberto Navigli. And what I've done so far is basically open information extraction and, well, more generally, disambiguation. That's what I'm going to talk to you about today. So this is how I'm going to split up the talk, roughly. So I will start by giving you some background of the work we're doing at Sapienza. This will also help me set up some context for what I'm going to tell you next. And then the two pieces of research that I've done, the FIE, or Open Information Extraction from Textual Definition, which was published like later in late 2015 in TACO, but that's actually the first work I've done as a PhD. And then KB Unify, a knowledge-based disambiguation and unification, which is actually a work that we presented at EMNLP last year. All right, so let's dive in. Brief introduction on us, on our group. Our group is called LCL, Linguistic Computing Laboratory. And we are the part of the computer science department at Sapienza who focuses on AI and NLP. I've been involved in a few projects, the main one being Multi-JEDI, which is a starting grant from the European Research Council, and also other projects with other universities like LEADER, still from the EU, which actually is more of a linked open data kind of thing, and a Google Focused Research Award, I guess in 2012 or 13, I don't remember exactly. But the core of our work, it's Multi-JEDI, which is actually not a Star Wars kind of thing, but it's an acronym that stands for Multilingual Joint Word Sense Disambiguation. And basically, the aim of this project is to enable large-scale disambiguation. Well, by large-scale, I mean large-scale in terms of languages, because we want to step outside of English and be able to do this kind of thing for as many languages as we can. And also in terms of scope, because in our community, you usually see that word sense disambiguation and entity linking are considered as separate tasks. But actually, they're kind of the same. Our claim is that they're kind of the same thing. The only thing that matters is actually the sense inventory that they use. And in fact, I would say the main output of this project has been the construction of such a research that would be able to integrate these two different kind of things. And this research is it's BabelNet. So BabelNet, it's basically, to the best of our knowledge, it's a semantic research that constitutes the largest multilingual encyclopedic dictionary and semantic network. It counts as much as 14 million entries in 271 languages. And it has like 380 million semantic connections. And basically, BabelNet was designed as an integration between Wikipedia and WordNet. Because, lexical knowledge from WordNet, which is, manually curated, lots of word senses, general concept, and so on, and then Wikipedia, so up-to-date word knowledge in many languages, and so on. But now, actually, today, BabelNet includes much more. I think as of version 3.5 includes 13 resources, actually very heterogeneous. And well, all integrations are performed automatically. Obviously, I don't have time to now tell you the story about this linking algorithm, but it uses semantic similarity and also machine translation here and there. The key thing is that BabelNet is composed of what we call Babel synset. We're sort of mimicking WordNet here, meaning that each concept inside BabelNet it's composed of a set of senses or lexicalization. But instead of being like WordNet only in English, they're obviously in multiple languages. And we also have a bunch of information more like taxonomic information. We have domain and categories drawn from Wikipedia. We have images, definition, translations, obviously, and so on. And also, each Babel synset, being BabelNet a semantic network, it's actually a node connected to many other things. So here you can see this snapshot here is a neighborhood of the node artificial intelligence. You can see a lot of things here: machine learning, Marvin-Minsky, only the closest neighborhood, I would say. And well, as a matter of fact, BabelNet I would say it's our core project, and we've built a bunch of things around it. First of all, we built a disambiguation algorithm, obviously. It's a graph-based disambiguation algorithm that we call BabelFi because it's entirely powered by BabelNet. It's unsupervised, and it's actually, I think, one of the first approaches who tackled jointly words-end disambiguation and entity linking, and this is actually a kind of an important thing for us. We have other things, and interesting things. It's, for instance, the Wikipedia by taxonomy, which is an iterative algorithm for the creation of a by taxonomy, which is a pair of taxonomies interconnected, one for the Wikipedia pages and one for Wikipedia categories. And much more things, which I would love to tell you about, but maybe another time, I would say.
Can you just give us a hint? I know you want to move on, but what do the precision levels of these various algorithms, like the automatic linking algorithm, look like? I mean, it might be a curve, but can you give us a sense of how?
So, if in the original paper of BabelNet, they were estimated around 90%, something like this. Now, that was the original paper of BabelNet, so it would only involve the mapping between Wikipedia and WordNet. Now we will have to probably do another kind of test with all the other resources, but I would think they would set pretty much on the same level, I suppose. But since BabelNet is now moving to industry and it's becoming a startup, we're trying to include other things like, for instance, crowdsourcing efforts and so on in order to increase levels of precision. But that will be the level, I would say. So let's go back to my research. So the initial motivation for what I've done, it's the following thing. It's the point that BabelNet was conceived more as a lexical semantic resource than an actual knowledge base. What do I mean by that? That basically, you don't have semantic relations. You don't have a way of knowing why, for instance, Pink Floyd and Adam Mahat's Mother are connected. You know that are connected. Also, Neil Armstrong and NASA, you know that are connected, but you don't know what's the semantic relationship between them. And so we thought, well, why don't we just turn BabelNet now into a proper knowledge base? And in order to do this, we thought to use open information extraction, which, being inherently unsupervised, actually fits perfectly with our way of working here. And so OIE it's great, but in order to be able to use it, there are too many issues that we have to face. The first one is sparsity, because since you don't have a predefined set of relations, the point that you may gather many relational phrases that express the same relationship because of synonyms, because of paraphrasing, because of many phenomena. And you also have ambiguity, because arguments and also the relation patterns themselves are ambiguous. Now, recent work on open information extraction has actually trying to deal with these kind of things, but I'll show you the way I tackled to solve these two issues. Let's start with DFIE. The main idea behind DFIE is actually fairly simple. We thought, well, why instead of targeting massive web-scale corpora and then trying to find a clever way of coping with the noise, why don't we just target smaller but denser and hopefully noise-free or much less noisy corpora of definitional knowledge? And once we do this, we can actually apply standard OI techniques to extract as much information as we can. In order to do this, we needed some tools. For sure, an underlying inventory, a sense inventory, because we want to perform a deep semantic analysis. We want to have arguments and also relation pattern linked to a sense inventory, to a proper sense inventory. Since we want to start from scratch from the input text, we need a disambiguation system, an entity linking system, or a worse disambiguation system, or maybe, actually both, if we have it. And then a syntactic parser, which is kind of standard component in many OI pipeline. And sense inventory, we use BabelNet. I've already told you about this, precisely because it includes both, let's say, graphing and encyclopedic knowledge, and this is great. And Babel 5 for disambiguation, which is the most suitable choice if you're working with BabelNet. As syntactic parser, we used CNC tools, which is it's a syntactic parser based on combinatorial categorical grammars. I don't know if you're familiar with syntax and syntax-related stuff, but basically this is not really a requirement. You could actually use a normal CFG parser or whatever parser you have. As soon as it has to produce dependency graph. That's it. So, but this kind of parser that are trained on CCG grammars are actually we found out that are suited to long-distance dependencies, and this is actually helpful. Let me show you with an example how the FIE works. So basically, we start from a definition. Atom Heart Mother is the 5th album by English band Pink Floyd. First thing we do is we perform both parsing and disambiguation in order to obtain a dependency graph for the sentence and a set of sense mappings for the sentence, meaning a mapping from fragment of the input text to BabelNet syntax in this case, because we're using BabelNet. Now, the thing that we do now is we're trying to merge these two pieces of information into a unified representation, which we call, syntactic semantic graph, which is actually, it's a fancy name, but it's not too complicated. It's just the same dependency graph that the parser produced, but when I have nodes that actually identify mention that have been disambiguated in the text, then I just replace those nodes with semantic nodes like those gray dots that you see here. For instance, album has been disambiguated, and then I attach the semantic information to the node itself. Obviously, here the point is that dependency graph are naturally encode word-to-word relationships. So, since the sense mappings could involve fragment on test higher than one token, then we have to somehow merge all these nodes together. And so, in cases like here, for instance, Atom Heart Mother, what we do is we replace the subgraph or the dependency graph that contains all these nodes with a single semantic node. And we do the same, for instance, for Pink Floyd here. This is the only caveat, but apart from this, it's a pretty simple representation. And then once we have this, we extract relation instances from this representation. We do it in a fairly standard way, I would say. We pick two entities, say Atom Heart Mother and Pink Floyd, and then we look for the shortest path that connects these two entities and includes at least a verb or a copula. So that will be X is album by Y, where X is Atom Heart Mother and Y is Pink Floyd. And this would be a triple that we extract. Another triple would also be this. X is Y, which is the easy relationship, still between Atom Heart Mother and album. And then we repeat, this process for all the definitions that we have, basically. Then what we do is, in order to construct relations, what we do is we just group all these triples by relation pattern, so that for each relation we have a relation pattern like this, and a bunch of argument pairs, like the one you see on that side. Here, a nice thing that we have here is that you may have relation patterns that are simple, like this, X is Y, but you may also have relation patterns in which some nodes are explicitly disambiguated, like X is album by Y. And this this thing will come in handy later, as I'll show you. What we do here is that, well, then we call all the left arguments domain arguments, all the right argument range argument. That's also fairly standard. And the next thing that we try to do is we try to characterize semantically this kind of relations by typing these x and y's, by giving a semantic class to x and y. For instance, in this case, we want x to be a record and y to be a band or a musician. So we do relation typing, and we do, and in the same way, we also want to score those relationships. Yeah, sure.
In the previous slide, when you recognized Pink Floyd as a band, the way you got there was in the previous slide you had Pink Floyd identified as an entity itself, right? So
yeah.
Is it true that all these Kaiser relations you already know from the previous? So you don't need to re-extract them. You already.
Which relation are you talking about?
Pink Floyd is a band. Is that what you used here to identify that Pink Floyd should go together?
Well, here, this is just what I get by running Babelfy on the input text. So Babelfy, I mean, it's a disambiguation algorithm, and this will tell me that this fragment of text refers to the entity Pink Floyd.
So it doesn't know that this entity Pink Floyd is a band.
Then, yeah, I mean, the disambiguation algorithm doesn't know, but once you've linked this fragment of text to BabelNet using this synth set, then you can retrieve all the information that you need. For instance, that Pink Floyd is a band, because BabelNet has also ESA information. And in fact, that's what I'm going to do in a while. Exactly to your point, what we're trying to, that's exactly the way by which we construct domain and range superclasses.
How do you know whether a sentence is a definition or a non-definition?
Well, for now, all we do is we assume that we have as an input a corpus of definition.
But it's Wikipedia based?
So, well, I'll show you later how the setup is, but yeah, Wikipedia is actually 80% of the corpus that actually we used in our experiments, in our experimental setup.
But only a fraction of those sentences in Wikipedia are actually...
The first sentence of each Wikipedia article.
Is that always true?
It's not. It's virtually true, because Wikipedia style guidelines suggest you to encode in the first sentence of a Wikipedia page a definition of what or who is the subject and why it is notable. So it's an assumption that many works actually do.
Do you have any idea how often the assumption is true?
I don't. Well, here we assume that basically it's always true. Actually, what we do is, I'll show you later. What we do is basically we use as input corpus the set of definitions in BabelNet, because BabelNet has a definition associated with each synth set. But many of those definitions are actually taken from the corresponding Wikipedia page. So it's an assumption that's made in BabelNet, and we borrowed that assumption basically. Maybe it's not always true. One could do that, but yeah, that could be a way. But yeah, here I would say the assumption is that we start from a set of definitions. Well, this of course is a limitation, and it's a great limitation, but the algorithm goes this way. You start from a set of definitions, and then you go. I would say, I mean, all the examples that I've inspected are fair definition. Actually, I think now Wikipedia has a kind of an automated way to produce the first sentence of a Wikipedia page somehow, in a sense that you specify the subject is this. It's this is for instance, if it's a musician, this is his nationality. This is I don't know, in the band in which he plays. And sometimes you have the Wikipedia page that constructs the definitions by itself. But well, of course, it might be that in a page you don't have a proper definitions at the beginning. Yeah, it could happen. But so basically, All right, so in order to type this relation, what we do is basically we consider, since we have arguments paired that are disambiguated, we use Babelnet to retrieve for each argument its hypernym, and then we construct for each domain and range a probability distribution by simply counting all those hypernym and normalizing. And this probability distribution, besides giving us a distribution of over semantic types for the two sets, we could actually use this distribution to have an idea of whether the relation is good and how much is good by looking at the entropy. Basically, the idea is given a domain or a range, a set of arguments, let's say, if that argument is the distribution of superclasses on this set has very low entropy, it means that it has very few entries with very high probabilities. And so it means that that's relation, that we assume that if that's the case, that the relation is semantically well defined. For instance, if you have X is album by Y, you would expect all X's to be records, let's say, and all Y's to be musicians or bands. So you would expect to have a distribution, well, ideally a distribution with only one element or two with very high counts. Vice versa, if you have a distribution in which you have many superclasses with very, very low counts and hence high entropy, then you may deduce that that relation is not really well defined. This is actually not always true. You may have very general relation like X is a Y or X is part of Y, in which domain and range are necessarily high entropy sets. And in fact, we actually devised an empirical measure to score relations in which you consider domain and range entropy, but also other things. Obviously, the total number of extracted distances. If one patterns let me extract a bunch of instances, many instances, then I assume that that pattern is correct. And also the length of a relation pattern, because we want to prefer shorter patterns against large ones. So here you can see, basically, that's the formula. The score is proportional to the number of extracted instances and inversely proportional to the entropy, because low entropy is good and high entropy is bad, to make it short. And also inversely proportional to the length, because the longer the pattern, the more likely it is that it's an error or some kind of these kind of things. Here's an idea of how the scoring works. For instance, if you look at the let's say at the first relation X directed by Y, it has presumably many abstractions, all definitions of movies. I would say I expect it to have a reasonably low entropy, because X in this case should be a movie and Y should be a director. And also it's fairly short as a pattern. It's only 2 tokens. But then you have a pattern like X known for Y, which is actually, it's well defined, but then X and Y could be anything, and so you have higher entropy, as you see in the third column. On the bottom, let's say on the bottom of the ranking, then instead you have something like very long patterns like X's village founded in 1912 in Y, which is it's a proper relation, but it has probably very few abstractions. The pattern it's so long. Well, the entropy is obviously low, because obviously X's are villages and Y's are regions or provinces and so on. This is not a perfect measure, of course, but it works fairly well. And finally, the last thing we do is we taxonomize our relations, because this is something that's not done very often in traditional OAE. It's not enough to have a set of relations. We also want to have this set of relations arranged in a proper way. We want to know that, for instance, if X is a solo album by Y, then X is also an album by Y or a piece of art by Y. It's actually an interesting thing that one could use, for instance, for doing inference. Actually, there are not many contributions that try to do this kind of thing, because usually it's fairly complicated. But actually, you have a very easy way to spot cases in which one relation is another relation. For instance, if you have something like this, if you have two relation patterns that are, let's say, exactly the same, same tokens, same length, same structure, except for a single node, for a single semantic node, then we can actually pick that semantic node and go into BabelNet and see what are the hypernyms of that node. And if one of the hypernyms it's actually the node that is in the other pattern, then we can fairly, in a fairly confident way, say that the bottom pattern is the top pattern. We could also make it even easier if the semantic node it's a multi-word expression. We could just strip off all the modifiers, and if we end up with the same word of the other pattern, then we can fairly confidently say that this pattern is this other pattern. I mean, these are astonishingly simple rules, but given the fact that we're focusing on a corpus of definitions, they actually work pretty well, and you're able to spot many kind of relationships like this, because definitions usually have a regular structure.
I'm confused a little bit. This is generalized, or this is a taxonomy of relations?
Yeah.
The taxonomy is about studio album to album. Is that not?
Yeah, since you have, so you already have the studio album is a album, and this comes from BabelNet. Since you have this, then you can say that this whole pattern, X is studio album by Y, is a X is album by Y. Basically, you infer that since the pattern is exactly the same, except for this node, but this node is a child of this other node in the BabelNet taxonomy, then you can conclude that the whole pattern, this whole relationship, it's a type of the above relationship.
That's the sort of standard generalization, right? Is this specific to relation? How is relation coming in? I guess that's when I'm confused here. This is the standard taxonomy, like if X is a dog, then X is an animal.
Well, that's what we're trying to achieve with this. We don't have this yet. I mean, this is a way of capturing easy relationship within relation patterns. Of course, it's a very simple way. I mean, you will miss many cases. It's enough to have a paraphrase of this to not be able to recognize it. But in fact, the point is, since definitions they mostly have let's say a common shape. Let's say you're actually able to spot many cases like this. You could make it fancier. Obviously, you can make it fancier in many ways. But with this, you already have a fairly high number of relations. The setup. So let me tell you about the experimental setup. As I already anticipated you before, in our experimental setup, we consider the whole set of English definitions in BabelNet, which is around 4 million 300, for more than 4 million items from 5 different sources. Well, there's Wikipedia, Wordnet, Wikidata, Wiktionary, and Omega Wiki, but most of them, I would say 80% of them actually come from Wikipedia. This is what we were saying before. I mean, it's probably not given 100% that each first sentence of Wikipedia page is a definition, but theoretically that should be the case.
An item is a proper noun or a noun phrase, or
What?
Is an item a proper noun?
No, by item I mean just an element of that set, just a definition. We have 4 million and so on definitions.
Are the things being defined restricted to any particular syntactic category?
No, they're just all the entries inside BabelNet, basically. You could have automat mother. You could have also general concept. You could have I don't know, the BabelNet syntax for dog, for instance, would have a set of definitions, and those are correct definitions that we include in this set. We try to consider as many definitions as we can, basically. I guess that's as far as I know, that's the largest set of definitions that is available, because precisely because it includes Wikipedia, many other resources, and so on. And well, basically, if you run the whole pipeline, that's what you get. Here's some numbers. You manage to obtain 255,000 distinct relation patterns, which is reasonably high. But the point is, you get as many as 20 million extractions overall. Which is 20 million triples, which basically gives you more than 80 extractions for relations on the average. And this is great because obviously here the point is, what we're doing here, we're not imposing many semantic constraints, many constraints to the data. We're just, let's say, trusting the data. And but the point is, even if you impose some constraints like other approaches do, for instance, also Patty and WiseNet. I don't know if Patty and WiseNet are recent OIE approaches, I guess 2013, 2012, which are also based on disambiguation. But yeah, the point is, all these approaches try to cope with the fact that data are noisy, and well, what we do is let's say we trust the data we have, and so we manage to have much higher coverage. If you think about, for instance, if I were to impose the constraint that maybe Patty and WiseNet do impose, and let's say I take away from this, I don't know, half of the extraction that I have, I still end up with 10 million so relations, which is, considering the fact that we're only using definitions and not whole pages, for instance, this is actually a bit surprising even for us. That's why we decided to publish this kind of work.
The number of extractions is the number of unique extractions?
Yes, the number of triples.
So that totally depends on the number of relations that you have, right? Like if, say, Nell, for instance, collapses 1,000 of the relations to be the same one, that will, by definition, reduce your number of extractions. Make sense?
Yeah, well, if you have even a triple, if you have like left argument, right argument, and then the relation, which is the middle argument, the same, that counts as one, even if you have multiple times, obviously.
So how do you know that, like, say, between def.ie and Nell, that Nell isn't just better at discovering synonymy between the relations, and that's why it has a lower extraction count?
Well, but that would be, in order to do this, you will have both arguments to be equal, but that doesn't depend on how you, even if you cluster relations. Let's say if I have, two or three triples that, for instance, def.ie split it in 3 different relations, that will count as 3 different relations and 3 different extractions. But even if you, if another system, for instance, merges these 3 relations, this still counts as 3 extractions because the argument pairs are different.
He's basically assuming that what you're describing happens less than 10 times per, right? Then it's more. If it happens 3 times. But what's the, there's no precision or quality numbers. So
Yeah. Well, we have them. Not in this table. Yeah, we performed a bunch of tests. Yeah, well, we have like precision and coverage evaluation, and also novelty of information. We did a bunch of tests, and precision we have comparable results than Patty, which is the closest competitor, basically. I don't remember now exactly the figures, but it's the same level around. Yes.
So in this table, is the third number the product of the first 2 numbers?
Yeah, exactly.
Then some numbers are wrong.
What?
Because like 255,000 times 81 is more than 20,600,000.
Well, that could be.
255 times 80 is 2,400 already.
No, 255 times 40 would be 10 million, times 80 would be 20 million. The numbers are basically right.
Yeah.
The numbers
Well,
are basically
I just multiplied it, and it's, you know,
yeah, the numbers right.
it's about 20.
Yeah, it could have been a typo. I mean, it definitely could have been a typo. I don't know if there is. Just great to know. I just
255, 881 times 81.68 is 220,900,000.
You need 300,000 multiplied by 80 to get 225 even 3.
yeah. I've been rounding. Obviously, I've been rounding up some decimals, but
So, but going back to your point about the precision being comparable to Paddy's, are you basically saying that what this method has achieved is an increase of sort of, 25, 33% in the recall over Paddy? Is that
Yeah.
the win due to DefI?
yeah, that's the whole point to me is what Patty does. It's tackles, like, for instance, an entire Wikipedia, and then enforces, let's say, a high precision setting, in the sense that it tries to find a way, to a conservative way of removing patterns that it doesn't like, and so on. Instead, we're kind of doing the opposite. We say, let's start from a clean set of definitions, and let's see how much can we get if we instead enforce a high recall setting, meaning that we're trusting the data as much as we can. That is basically the idea.
So that seems like a good idea, but it sounds like you're not saying that the algorithm is particularly better. You're just saying you're running it on a different data set. What would happen if you ran something like
the algorithm? Yeah, but in fact, I mean, this kind of system, I see it more like an experiment than I would call it a prototype, because I mean, you may have much fancier way of, for instance, extracting relations, constructing the relation taxonomy, and so on. Yeah, definitely. Yeah. It's the algorithm. Well, it's a full pipeline that goes from scratch to relation taxonomy, and this is great. But I mean, apart from the syntactic semantic representation, that kind of thing that we had, it's not like something that's far beyond standard. It's really, I mean, the extraction system, it's not much different than Reverb one, for instance. You take shortest path, each shortest path that contains a verb, and
It illustrates your point that definitions are a useful data.
exactly. That's where I'm trying to get, basically. That's why I was saying, even if you, okay, let's say this is a very high recall setting. Let's say we impose some constraints, like, for instance, each pattern doesn't have to start or end with a modifier. That would be fairly reasonable. Even if you remove millions of instances, if you consider that we start from 4 million and so on sentences instead of, for instance, 4 million and so on articles, this still illustrates the point. That's what we're trying to show. Yes.
So if I understood correctly, if you extract X as a studio album by Y, you would also populate in your extractions X as an album by Y, X as a piece of art by Y.
Yes, you will achieve that because you have actually X is and then BN something by Y. That BN something, it's a concept of album inside BabelNet, which contains all the lexicalization of album.
So how much does that contribute to this 20 million? I'm thinking because you could also do this at inference time instead of doing it in advance.
Well, we didn't compute figures to estimate that, but I think that's I don't know. I wouldn't know, but I think in many cases it would do these kind of things, because,
right,
for instance,
imagine, like, for everything you probably have 3 or 4 things above in the hierarchy, so the actual extracted things are probably.
yeah, but not only in the hierarchy, you also have many synonyms. That's actually, when you extract relations, you actually consider only the synonym. It's only when you construct the relation taxonomy that you consider the hypernym. But for instance, if you have the concept of village, X is village and Y, then village could be, I don't know, town, and all the synonyms that you have. So whenever you find, like, X is a village, X is a town, X is a, I don't know how many synonyms there are, but all those will be merged in in the same relation pattern. That's the thing. And then obviously, since you consider the shortest path in a dependency graph, you're stripping off all the modifiers. So X is the first album by Y. X is the last album. X is a successful album by Y. These also contribute, obviously. And then, another interesting thing is that we have the number of entities. It's reasonably high, and that's because we're using joint words and disambiguation entity linking. So we have both general concepts like, for instance, album in the previous example, and obviously entities, which is very nice. And compared to Patty, with the two simple rules that I showed you to construct the relation taxonomy, we basically doubled the number of edges already. And this is great because Patty uses a complicated method to construct the taxonomy, which is based on identifying subset relationship within domain and ranges of relations pair. Already with these two simple rules, we double the number of edges, and this is great. Then, as we were saying, we have we did a bunch of evaluations more. But really, as I was saying before, the point is not really in achieving like the best result. You could actually improve a lot. You could do relation clustering, as in Patty and WiseNet. You could do fancy way of computing hypernymy relationship. You could do I would say a larger step would be trying to achieve multilinguality, because we're using a multilingual sense inventory, and we're using a multilingual disambiguation algorithm, and we also have we also have a multilingual set of definitions in BabelNet. So I mean, in this case, we're only using English, but for each synthesis inside in BabelNet, you also have definitions in the other languages. I mean, we're just one step away to trying to turn this kind of a system in a multilingual system. And obviously, I mean, you can try to start from the relation that we have and do some relational learning to try to come up with a model of each relation, and also perform like A/B completion and these kind of things that are actually very popular in these days. And you could also think, obviously, you could think about scaling up this thing to general text, not only definitions, because obviously, as we were saying before, we are assuming that we have a set of definitions. So either we, for instance, we tackle the web and we try to identify definitions inside pages or inside articles or whatever, or we try to adapt this thing to general text. But obviously, these are two ways of overcoming this assumption that obviously is restricting, because once you step outside definitions and you have subjunctive clauses, you have fancier ways of defining terms or describing terms, then obviously you cannot enforce this very simple pipeline. But that's it, basically. Last thing I wanted to talk to you about is it's another work that I've done together with a colleague of mine at the University of Barcelona, and it's called KB Unify. So the idea here, it's so we have you know much better than me. We have many open information instruction systems. Some of them produce linked resources, like Patty and WiseNet, in the sense that arguments are linked to a sense inventory, which could be Wikipedia, could be Freebase, could be DBpedia. Others produce unlinked resources, or resources that are linked to their own ontology, like NEL. But the point is, instead of coming up with yet another open information instruction system that produces yet another resources, why don't we start from the output that we have from all these systems and try to obtain a unified resource in which you have a unique sense inventory that basically covers all the individual resources, and instead of having just a relation pattern, you have a relation synset in which you merge together relation patterns that come from different resources, but actually express the same relationship. So that was basically the idea that we had. And well, again, in order to do this, we needed some tools. A unified sense inventory, obviously, because we want a unified knowledge base to have a unique inventory in which we don't have duplicates in terms of triples, for instance, just because they're defining with respect to different inventories. A disambiguation system, because we have resources that are unlinked, and we have to find a way to actually connect them to a sense inventory. And then the key thing here is we're also using a unified vector space model. What do I mean by this? Basically, a model that is able to associate with each element in our sense inventory a vector of real numbers defined in a metric space. And this will be key, as you will see in a moment. Well, the first two tools, you already know them. You no need to talk more about them. As a unified vector space, you could use many things. What we used is actually a recent work that was developed in our group and presented at ACL last year. And it's called Sense Embed. And it's basically an embedding model that is sense-based. It's like the popular Watervec architecture that is the skipgram model. But instead of being trained on a normal corpus, it's trained in a sense-annotated corpus, so that you actually obtain latent representations for senses. Obviously, if the corpus is annotated with respect to BabelNet, then you obtain latent representations for BabelNet senses. And this is the representation we use. You could use others. For instance, you could think about other type of vectors. You could use also word embeddings instead of sense embeddings, and then try to find a way to represent a sense by, I don't know, averaging the vectors that you have for each synonym, and so on. You may have different ways. This is the way we did it. Let's see basically how it works. So we start by distinguishing those resources that are linked and those resources that are unlinked. And then we perform two steps. In the first step, we try to redefine all these resources using the same sense inventory. All these individual resources using the same sense inventory. And this is actually, this could actually be done in two ways. If the resource is linked already, then the job is actually done, because we can actually exploit the mapping inside BabelNet from and to Wikipedia, Freebase, DBpedia, and so on, to directly map these resources, KD1, KD2 in this example, to BabelNet. So that will be easy. But then when you have unlinked resources, you have to disambiguate them somehow, and that's really tricky, because we're not talking about disambiguated pieces of text. We're talking about disambiguating triples, and that's not obvious how one could do it. Let me just go deeper into this disambiguation thing. So basically, the way we decided to disambiguate is based on two intuitions. The first intuition is that if you have a bunch of triples, let's say in the target knowledge base that we're trying to disambiguate, you may have some triples, obviously not all, but some triples that are easier to disambiguate than others. So for instance, if you look at this triple here, you have Armstrong works for NASA. Then Armstrong is ambiguous, because that could be obviously an astronaut, that could be a musician, that could be a cyclist. NASA, it's also ambiguous. I think in BabelNet it's ambiguous. But the point is, even though they're both ambiguous, if you find those two together, then you would expect that this Armstrong refers to the astronaut and NASA refers to the space agency. And so there are two candidate meanings for both arguments that are related much more than all the other candidates. This is one intuition. The second intuition is that, in general, you should have two disambiguation strategies that vary according to how much a relation is specific. What do I mean by this? That basically, if you have a relation that's specific, like, well, X is outbound by Y, or X is capital CD of Y, then you have all the domain arguments and all the range arguments that are related to each other. Because obviously, if you have X is outbound by Y, all the X's will be the albums, and all the Y's will be musicians or bands. So you have that inside the domain set and inside the argument set, all arguments are somehow related. And so those could provide meaningful context when it comes to disambiguation. Instead, if you have a much more general relation, for instance, I don't know, X is part of Y, then that's not the case, because X could be anything, Y could be anything. And so domain arguments are not related to each other, and range arguments are not related to each other. So in this case, if you have to disambiguate triples, then it's much safer to disambiguate them one by one, because you would only bring in noise if you had to bring them all together. So those are basically the two intuitions. So based on these two intuitions, basically the algorithm we devised, it works like this. So it's a relation-wise algorithm. So for each relation inside a target KB, what we do is first we try to identify those relation pairs for which intuition 1 is true. That is, those relation pairs for which you can, with high confidence, identify the candidate meanings that are related. And then once you have those, you disambiguate using those senses. Once you have this set of seeds, then you try to model the specificity of the relation by looking at how these seed arguments are distributed in the vector space. This is a way to estimate how a given relation is specific or general. Based on this estimation, you then say, well, if the relation is specific, then I disambiguate all the relation triples at once. Instead, if the relation is general, then the only thing I could do is disambiguate each triple by itself. So first, let's go with point 1. So how do I identify seed arguments pair? Let's take this example. The previous example, Armstrong was for NASA. You have 3 candidates for Armstrong, and let's assume that NASA is unambiguous. For each candidate, we retrieve their corresponding vectors using sense embed, and then we just compare pairwise. I mean, we just look at all the possible pairings of candidates. So VD1 with VG1, VD2 with VG1, and VD3 with VG1. And if the triple is good, that is, if the one of those triples for which 2 candidates meaning are more related than all the others, then you would discover it by computing, for instance, similarity measures between the 2 corresponding vectors. For instance, cosine similarity. Look for the highest value of cosine similarity and for the pair that maximizes this cosine similarity. And basically, in this way, you're able to spot the correct disambiguations. Then, obviously, for each relation, you try to identify these cases. Obviously, you would have an answer in terms of cosine similarity for any triple. So you have to actually consider a threshold and keep only those that are confident enough. But this would help you gather a subset, even a tiny subset, but a subset in a given relation of argument pairs that are easily to disambiguate than others.
5 minutes.
Oh, okay. So just go super fast. Well, basically, what you try to do then is compute the centroid of the domain and the range, and look at the variance of the seeds in the vector space. And what you do, what you see is that if you have the seeds that are spread out in the vector space, then you conclude that this relation is general. Otherwise, you conclude the relation is specific. And this is basically how it goes for disambiguation. So this is it's a high-level look at the process. Start from the linked triples, identify some disambiguated seeds, rank by specificity, and then if it's general, disambiguated triple by triple. Otherwise, disambiguated all the relation altogether. And then finally, once you have all relations that are defined, redefined with the same sense inventory, then what you do is we try to align relations at this point. And this is, in order to do this, you rely again on the vector space. So basically, it's a matter of representing, given two relations that come from two different recesses, you represent them in the vector space using their centroids, and then you simply compute centroid similarity between the two domain centroids and between the two range centroids. And basically, it's as easy as that. Then you can see that basically if you have domain centroids and range centroids that are close enough, then you will say, well, maybe these two relation patterns actually express the same relations, and you merge them in a same cluster. Otherwise, you just keep them separated. And that's basically it. This is the whole thing. I don't have time now to show you all the. I did have some slides on the evaluations, but well, basically consider the same system that I showed you in the previous part. You have some numbers here about seed precision and coverage. I really don't have time to cover this. An interesting thing that I would like to show you is that the intuition about specificity. We actually, to have a feel of whether it worked, we actually plotted it by considering the generality of R, which is the measure that we computed, against the average argument similarity of the relation. And you see that basically, when a relation is general, the average argument similarity goes down. And if you actually inspect a bit this graph, you will see, for instance, in Nel, you would see that up high, yes, among the specific relations, you have something like X restaurant in C dy. For reverb, we have X enter Taurus in Y. For Y, you have X lobfin fish living during Y. If you go down and look at the bottom part of the graph, you have something like, for instance, in Patti, X located in Y, or X is a type of Y in YSNet, or X agent created Y in Nel. And then obviously, well, we evaluated also the alignment, but there are some nice examples actually of alignment that actually, since you don't rely on the shape of the relation pattern itself, but only on the characterization of its domain and ranges in the vector space, you are able to spot patterns that are actually quite different in terms of syntactic structure, for instance, and merge them in the same cluster. So, for instance, portrayed and X's character in Y, debuted and first appeared, animal eat food, feeds on. So, as a selection of and offers. Now here, basically, the same story goes as for the other approach. So it's not. This is really not like the best. It's really the best way of doing it. You may come up with fancier way, for instance, of aligning relations. You could think of an iterative algorithm that performs disambiguation and alignment in the same way, instead of one after the other. Kind of using an EM style in which you first do one, then do the other, and then you iteratively go on and refine both steps, and so on. But basically, so jumping straight into the conclusion, what I presented to you is these two systems, a fully fledged DefIE, which is basically a pipeline for a fully fledged pipeline for OIE targeted to definitions, and then KB Unify, which is an approach to knowledge-based unification and disambiguation, which is based on the sense-symmetry equivalent and on a vector space model. So, but what basically the take-home message that I wanted to convey here is that, all right, we have OIE, web scale OIE is absolutely great, and it's definitely the way to go. But sometimes it's worth stepping back and having, for instance, a look at from where are we starting data. And so definitional knowledge is important. It's the same quality versus quantity trade-off as always. And also that making sense of the output of HOI is important. So you can use semantic analysis like we did and see how different OIE output can actually speak to each other, let's say, and benefit from the fact that you actually can connect them. So you can have a mutual enrichment from this process. So basically that's it. Obviously, I don't know if you have time, but if you have any other questions, I had to go very fast, but if you have whatever curiosity or question that's left, just I'll be happy to.
Well, you're here throughout the day. Thank you very much.
Thank you.